Next, we're going to talk about how to use ordinary bivariate generating functions to calculate moments. Now, this section has quite a bit of calculation in it, quite a bit of math on the slides, and they're a little bit more for reference than for me to talk about. But still, many of the calculations are familiar, and I think you'll see that it's worthwhile to include all the details. But really, I don't want all that math to obscure the bottom line that actually it's very easy for us to calculate moments once we have a good expression for the ordinary bivariate generating function in many cases. So I'll go through the details in this section, and then in the next section we'll see lots of details that illustrate how simple the calculation can be. So we start off with the ordinary bivariate generating function that we defined for combinatorial classes with parameters. We sum over all objects in the class, z to the size of the object, u to the cost. And we have our elementary identity that I'll write over on the right. I'll write more classic probability expressions just for reference and for checking the kind of manipulations that generating function manipulations that we'll be doing. So the first thing is enumeration. So how many objects are there of size n? That's the sum on k of p and k. So sum over all costs, the ones of size n, you get the number of objects of size n. From the ordinary bivariate generating function, how do you get that? Well, it's just the coefficient of z to the n in the bivariate generating function evaluated with z equals 1. So that's p of z1, then the u goes away, it's all 1. It's just sum on p, everything in the class, z to the size of the class. But again, that can be collected with all the ones of the same size. That's exactly the same as p sub n z to the n. So p sub n is the coefficient of z to the n in the ordinary bivariate generating function evaluated at u equals 1. Or you can do the sum and substitute p and k in there again and get back to p of zu. Okay, so that's enumeration. And again, this math over here is not really needed except to check your understanding of what's going on. Now let's look at the cumulated cost. The way that we compute averages when using generating functions is take the total cost in the objects of size n and divide that by the number of objects of size n. That's the average. That's a little bit different calculation than working with probabilities, but since we have this powerful mechanism for counting and for getting counting results, it's natural to do it. And we can see from the ordinary BGF how this works. So we're interested in the total cost in objects of size n. So again, that's for all values of k. We multiply the number of objects of size n that cost k by k. That gives the cost for all of those objects, and then we sum over all values of k. We'll just call that q sub n. What's that value in terms of the generating function? Well, what we do is we differentiate with respect to u, that's the marker variable for the cost, and then evaluate at z equals 1, at u equals 1. So that's the partial with respect to u of the ordinary bivariate generating function evaluated at u equals 1. Just from the definition, that's the sum on all objects, the cost times z to the number of objects. And again, if you collect all the objects of a given size n, that's exactly the same as q sub n z to the n. So it's the coefficient of z to the n in the partial with respect to u of the OBGF evaluated at z equals 1. Or you can look at this representation on the right of the generating function. This one at the top. If you differentiate with respect to u, it brings down a k, so that you get k, p, and k. And that's the familiar way to think of the total cost. But in terms of the bivariate generating function, it's a simple partial derivative and then evaluate at 1. So that gives us what we need to calculate the mean cost of objects of size n. We take the coefficient of z to the n in the partial with respect to u of the OBGF, evaluate at u equals 1, and divide by coefficient of z to the n in the OBGF evaluated at u equals 1. And that's, in many cases, a simple calculation. And again, that's the average, which maybe you're more familiar in the form over here, Kp and K over Pn. And we can calculate then the variance in the same way. Definition of the variance is the sum on k minus the mean squared times the probability. In terms of the ordinary bivariate generating function, it's not hard to check that that's the second partial with respect to u evaluated at z equals 1, and subtract off, add the mean, subtract off the mean squared, just as with normal probability calculations. So that's a overview of calculating moments from an ordinary bivariate generating function, just using partial derivatives with respect to the variable that marks the cost, and then evaluating at that variable equals 1. And we'll look at example next. So this is our bit strings example for what's the number of 0 bits in a random binary bit string. We talked in the last section about our construction and the OBGF equation, 1 over 1 minus z times 1 plus u. So now we'll start with that equation and calculate the average number of 0 bits in a bit string. And again, we know the answer to this. It's going to be half of them, but this will illustrate the calculation, and we'll use the very same straightforward method for more difficult problems. So how many binary bit strings are there? Well, we evaluate at u equals 1, so that's 1 over 1 minus 2z, and then take the coefficient of z to the n. That's 2 to the n, so that's as expected. To do the accumulated cost, the total number of 0 bits in all bit strings of length n, we need to compute the partial with respect to u of the OBGF. So to compute the partial with respect to u, it's 1 over 1 minus zu. All that's relevant is the minus zu, so it's that to the 1 minus zu to the minus 1 power. So it's minus that squared, and then times a minus z, the two minuses cancel, so the partial with respect to u of that is over here on the right, z over 1 minus zu squared. And to calculate the accumulated cost, we just evaluate that at u equals 1. So at u equals 1, that's z minus z, 1 minus 2z squared. So we want, for the accumulated cost, the coefficient of z to the n in z over 1 minus 2z squared. And that's an elementary calculation from power series that it's n times 2 to the n minus 1. And so now the average is just divide those two, and that's n over 2, as expected. So it's just computing the partial with respect to u, which once you've practiced a few times and remembered the definitions, it's not so difficult a calculation at all. And it's certainly one that can be done automatically nowadays. So we're not going to compute the variance because there's an easier way to do it that we'll talk about in just a second. Okay, now I mentioned the idea of horizontal and vertical generating functions that go with bivariate generating functions. And so now I want to take a look at moment calculations using these methods. So let's look at the moment calculations in terms of the horizontal ordinary generating function. So that's a generating function that gives the cost for an object of a given size. So what we do is we take the coefficient of z to the n in the bivariate generating function, and we'll call that a little piece of n of u. It's a generating function for the cost in all the objects of size n. And it's just the sum over all objects that are of size n, u to the cost of that object. And again, the cheat sheet over here in the terms of P and K, that's sum on K, P and K, u to the K. So it's the generating function for costs. And so that's only got one variable. And since we're interested in knowing the number of objects of size n and the average number of 0 bits in objects of size n, we can use that generating function directly to get the answer that we want. So the first enumeration, if you evaluate that at u equals 1, you get the number of objects of size n. So that's just evaluated at u equals 1. It's summing for all values of k, the number of objects of size n that cost k, that's equal to the number of objects of size n. So this PNU is a useful thing for both enumeration and for accumulated costs. If you just differentiate that function and evaluate it at 1, then it's some k p n k, which is your accumulated cost, qn. So if we know that PNU, evaluate at 1 to enumerate, differentiate, evaluate at 1 to get the accumulated cost, and just divide those two to get the mean. An even simpler calculation usually. And then the calculation for the variance just involves the second derivative, and again, that's easy to check from the definition of the variance. So this method, using horizontal ordinary generating functions, is the one that we use most often to calculate average values and other moments of parameters. So let's look at using this example for 0 bits and bit strings. So again, that's our starting point, the two-variable ordinary bivariate generating function. The horizontal version is the coefficient of z to the n in that. Coefficient of z to the n in that is 1 plus u to the n. It's equal to sum of over n of z to the n, 1 plus u to the n, and so that's coefficient of z to the n. That's our horizontal ordinary generating function. So now we can do the two steps to get our average. First, enumeration, evaluate at 1, you get 2 to the n immediately. U equals 1, 2 to the n. To get the cumulated cost, we differentiate with respect to u and then evaluate at 1. So differentiate with respect to u brings down an n, and then evaluate at 1, 2 to the n minus 1, immediate. And so the average is the ratio of those two, which is n over 2, as we expect. And then taking the second derivative and then adding the mean, subtracting the mean squared, immediately get n over 4. And that's an easy calculation that tells us that the standard deviation is square root of n, the average is n, and what that means is that the distribution is concentrated. A typical value is going to be close to n over 2. And I'll talk in just a minute about what that means. For now, the point is that given a two-variable OBGF, if you can extract the coefficient of z to the size, then you get a generating function that's easy to work with to calculate moments. Now we can also do moment calculations with vertical ordinary generating functions. I put this slide up for completeness. I'm not going to spend a lot of time on it because actually in the lectures we're not going to do any derivations this way. But it's the same idea, just on the other variable, the vertical instead of the horizontal. If you take the coefficient of u to the k in the ordinary bivariate generating function, you get the generating function for the costs of objects of size k. And it's the same idea, just holding the cost constant. And that's sum of p and k z to the n. And so to enumerate, we do it the same way with the bivariate generating function, but accumulated cost is a coefficient of z to the n in sum of k qk of z, where qk of z is the bivariate generating function. So we have to extract another coefficient, but there's some problems where it's easier to do the calculation this way. And so it gets down to the mean again, and you could do the variance the same way, but I'm going to skip it. And again, this is just for completeness. This is not the way to determine the average number of 0 bits in a binary string, but in some mechanical ways you might do it, and it illustrates the idea. So if we pull out the coefficient of u to the k, we get the vertical generating function. In this case, it's z to the k over 1 minus z to the k plus 1. Then we enumerate same way as before to get the 2 to the n, but the cumulated cost is coefficient of z to the n in sum on k times the vertical OGF. And that's a familiar geometric series with an extra factor. And here's the details for those of you who are used to those sums. That sum evaluates to z over 1 minus 2z squared. And the coefficient of z to the n in that is n to the n minus 1, so we get n over 2 as before. And again, in this case, it's more work to get the same answer, but there's some cases where it's less work. And it's just a matter of the order in which we extract coefficients. Usually, it's better to use the horizontal where we extract the coefficient z to the n first. And in this simple example, we're always getting n over 2. So why the focus on the moments? Well, we're always interested in the average. What value can we expect? This is classical in probability, so I'm just going to take a slide to mention these classical results. So if we have a random object of size n with mean mu sub n and standard deviation sigma sub n, then we have these famous inequalities, the Markov inequality and Chebyshev inequality. It says that the probability of being much larger and smaller than the mean must decay. And an upper bound on the rate of the decay is measured in units given by the standard deviation. That's why the standard deviation is important. So Markov inequality says you're not going to be too many standard deviations away from the mean. The Chebyshev inequality says that the probability that you're t standard deviations away from the mean is less than 1 over t squared. Actually, we can get much more accurate results than these for many of the things we study because we have the full distribution. But still, the basic idea is the same. And what we say is that if the standard deviation is of smaller order of growth than the mean, then we call the distribution concentrated, because it means that as n gets larger, the average value tends towards the mean. We can think of the mean value as a typical value. We could calculate out some specific bounds, but usually it suffices in the analysis to learn that the distribution's concentrated. And we move on, knowing that we could do more detailed analysis if we want. So this is just a formal statement of that. If a distribution is concentrated, then your value of your random variable over the mean approaches 1 in probability in a very specific sense. So when it's concentrated, we just say the expected value is typical. That's the one that you really do expect to get. And this is just an example for our random bits. If you have 100,000 random bits, you expect about half of them to be 1 bits and about half of them to be 0 bits. The standard deviation is of that, it's square root of n over 2, so it's only about 5,000. So that says that the probability that a random value that you get is between 49,900,000 and 50,100,000 is better than 99%. That's the kind of result that we want in practice. With really high probability, we have a good idea of what the value of the random variable is going to be. That's why we care about concentrated. So this is just a plot of this distribution, which is the binomial distribution. As n increases, there's another curve. And so what it shows is that as n gets higher, the curves come tighter and tighter together towards the mean. So that's just true in many, many cases. In fact, this particular curve describes lots of distributions. We'll get to that later. All right, so here's just another example, really generalizing our number of 0 bits example. So let's talk about the class of all m words. So that's just strings with every integer between 1 and m, or sequence of sets, as we talked about last time. So the size, again, is going to be the number of letters or the length of the word. But let's take as a parameter the number of occurrences of a particular letter in the word. So that's our bivariate generating function. So now to construct that, we use u to mark one of the letters, a particular letter. And then we don't mark all the others, so that's m minus 1z. So we had m equals 2 before, we had uz plus z. Now we have general m, it's m minus 1z. And that immediately translates to 1 over 1 minus m minus 1 plus uz. We have m minus 1z and a uz, and that's it. So now that's our ordinary bivariate generating function. If we want to enumerate, we just evaluate that at u equals 1. Evaluating that at u equals 1, and then we want the coefficient of z to the n, and 1 over 1 minus mz, that's m to the n. So that checks. And if we want the cumulated cost, we differentiate with respect to u and find the coefficient of z to the n. And that's the same kind of calculation that we just did for 2, and we get n m to the n minus 1. So the average number of occurrences of a given letter in a random m word with n letters is n over m. And again, that's as expected. And we can also go ahead and compute the variance, and it's n over m minus n over m squared. And the square root of that then is proportional to the square root of n, so it's concentrated. And that's a direct analysis using the symbolic method, followed by calculations using partial derivatives, the basic method that we're going to use to evaluate parameters. And I mentioned the practical application of hashing algorithms, and this is from our algorithms books or Knuth's book or any book on algorithms, where we organize a table of values by hashing them to random values between 0 and n, and put our n items into m keys, and we're interested in the length of all the lists because we're going to have to search the list sequentially. So that's the strategy, and then we're interested in what's the average number of keys on a list. And again, it's trivial that the average is n over m, but that's also what we just proved with the symbolic method. But the extra analysis to get the standard deviation tells us that it's concentrated, which means as n increases, it's going to that value is going to be typical, and that's useful to know in practice. And we're not likely to have that case where they all fall on one list and nobody falls on the others. So that's just one practical example in many, many of the applications that we look at. What we want to do is find the average value, show that the standard deviation is of smaller order, and that's the case in many, many, many of the applications that we study. So that's the process of calculating moments from the ordinary bivariate generating function. And again, with illustration from familiar binary numbers, but also one practical application. Next, we'll look at applying these same kinds of calculations in other applications.